Titled Storage Replication in High Performance, High Availability Environments. And before I start with getting into the talk proper, I'd like to get a little bit of a feel from you guys who's been working with what kind of stuff that I'm going to be talking about in the next 20 minutes. So those who are here, I presume most of you, otherwise you probably wouldn't be here, have already dealt with or worked with HA solutions on the Linux platform, right? Can I have hands for that? Who has? Okay, plenty, great. Of those, who of you guys is familiar with the pacemaker-based Linux cluster stack? Quite a few, great, okay. Who of you are familiar with storage replication technologies of whatever kind? Could be DRBD, but doesn't have to. Stuff like SRDF or Metro Mirror or whatever they call continuous access. Okay, quite a few. Okay, and who of you have worked with or are familiar with hardware RAID solid-state caching technology? This goes by a variety of brand names such as LSI Cachecade or Adaptec Max Cache. Have any of you worked with that in storage arrays? Okay, a few. Great. Who of you has, prior to this talk, heard of this thing called flash cache? Okay. Any of you here currently running flash cache on one of the servers or systems that you manage? One, great. Okay. So besides those two, who of you uses flash cache at this point? None? Right. Or so you think. Who of you currently has a tab open in a browser window that is displaying this conspicuous logo somewhere? Some obscure website, some of you may have heard about it. There's only about 800 million people that are on it, allegedly. So this is where flash cache originally comes out of. Flash cache is originally a development at Facebook. The primary developers at Facebook are, I hope I'm not butchering his name too badly, Mohan Srinivasan and Paul Saab. And there's some significant input that's gone into the project also from Vadim Tkachenko from Percona. So those are the primary drivers there. Facebook is, and I guess this is not surprising, they're a bit reluctant to disclose what they actually use it for, but what's publicly known is that at least originally they developed it for MySQL InnoDB data storage. MySQL with the InnoDB backend or storage engine at the time had this issue of when you shut a MySQL instance down and brought it back up, if the database was reasonably large, then for quite a significant amount of time immediately after the boot up, because the thing would be operating out of cold caches, it would be significantly slower than when it's running with warm caches. In other words, when the server had been running for a while. And of course, that's not a good thing for a setup for Facebook, which has tons and tons and tons of data, which has to be served really, really, really quickly, and where nodes occasionally just go down. It just happens. So that's what it originally comes from, but it's not in any way InnoDB or MySQL specific. It's just a generic block level caching storage for the Linux platform. I'm going to get to how that's implemented in a little more detail in just a little bit. Okay, so what's this good for? Suppose we've got tons of data that we need to serve, and we need to serve it fast. Facebook is a sort of an extreme example of that. But there's a bunch of applications for which that is the case. You just have hundreds of gigabytes or terabytes of data in your general data storage, but you need to also serve that reasonably quickly. Now, one way to do that is you can just basically toss money at the problem until it goes away. Money in this case being hardware. So what you can do is you can just take that amount of storage that was previously in relatively cheap, at least in a dollars per terabyte view, storage arrays, and you just toss all of that into SSDs. this is something that you could call, perhaps the 1%er approach. There's not too many companies that can actually afford that. For most people, this sort of approach where you're just strictly throwing hardware at the problem is hardly cost effective. So what if we could go ahead and combine a relatively fast but smaller and arguably expensive SSD, combine that with humongous but slower and cheaper storage box. And that is exactly what Flash Cache does for us. LSI CacheKate or Adaptec Max Cache do the same thing, but they do that in controller firmware, and that is in a reasonably closed and proprietary fashion. And in Flash Cache, we can do that in a much more open way and a much more generic way, and in software and in Linux. So really what Flash Cache is, it's relatively simply a device mapper target. Device mapper is something that pretty much all of you are going to be familiar with, if not for anything else, then for LVM. The device mapper infrastructure is, of course, the underlying layer in the kernel that makes something like LVM possible. And of course, it's a pluggable architecture where you can just add new modules, and then those can provide additional types of device maps that are then exposed to the rest of the system as simple block devices. So it's a simple device mapper module called DM Flash Cache, and it comes with a handful of userland utilities. Currently 4, a fifth one is just currently being merged. So you get a number of utilities that just install into user SBIN, and you use one utility is called Flash Cache Create. You initialize basically the backing device and its cache devices. It has a boatload of options where you can fine-tune the cache as well. And then you have another thing that's Flash Cache Load, which simply activates this device and puts it into a device map, and then the device pops up under def mapper, and then the device name as you would expect from any device mapper module. And after that, we can simply use this thing as we would any other block device. So the canonical way of doing this would obviously be to just slap a file system on top of it. But this being a block device, you can use it for anything else that you could use any other block device for, including, by the way, something like an LVM physical volume. So how does the data flow through this kind of device now actually work? Consider for a moment that we're reading, say, I don't know, let's say we're reading 1 gigabyte of data at offset 42 from a specific from this device. And what this thing will do for us is, assuming we've just brought this thing up, it's not going to be in the cache, it's just going to be on the local disk array. It's going to go there and going to get that 1 gigabyte that we're about to read from offset 42, serve that up to the application, but at the same time also write a copy of that into this solid state cache. And then the next time we need to hit the disk, which means we're not only reading that same area of data, but it's also either no longer in our RAM page cache, or it's been invalidated in the page cache. Next time we need to actually hit the disk to read this, we don't have to hit the slow storage array. Instead, we can serve that pretty much immediately from the caching device. And that's a really, really nice trade-off that we're getting there. We don't have to toss money at the problem quite as badly. We don't have to spend as many bucks for it because we don't have to replace the whole thing with SSD. We're just putting stuff on SSD that's sort of the most important. This thing just employs a regular LRU, at least recently used cache. So stuff that hasn't been used for a while just gets evicted from the cache, and the newer data gets put into it. And even if you got something like half a terabyte of flash RAM here, that's still a pretty good performance improvement, and your data set that's actually being used and updated regularly, or even being read regularly, is quite likely to actually not exceed that. in many, many applications. Now, when we want to use this in a high availability environment, there's two options for doing this. And by the way, I'm only going into the DRBD side of things here, because obviously if you want to do this with more proprietary applications that you can, or a more proprietary approach, that you can do that as well. So you would be using something like Cachecade in the controller and then some super expensive replication facility between two storage subsystems. But the canonical way of doing this in Linux is simply with DRBD. So the simple approach here is you take one DRBD device and you simply stack that on top of two flash cache devices, one on the one node and one on the other. And the way that DRBD works, we just get synchronous replication between these two. Anything that we're writing goes into the flash cache device. Anything that we're reading comes from the flash cache device, and that way we can significantly speed up the process. But there's really nothing new to this. It's just because you can use any backing device, any block device as a DRBD backing device, this thing is essentially a no-brainer. It's really, really simple. It has a downside though, and that is, consider what I said earlier. You have an application, and this is by the way by no means InnoDB specific, or MySQL specific for that matter. Your application, when it's running off of cold caches, it's going to be slower than it was running off of hot caches. So when you fail over, remember, you've got a DRBD replication between these two nodes. You fail over to your other node. All of your data is going to be there. DRBD is going to make sure that that is the case. But because DRBD has no updates to do on reading, now when you fail over, the cache is cold on the other side. So after that failover, you can be expected to take a performance hit, which is of course a lot better than being down, but in many applications that's unacceptable. You want to be up to your full performance and not take a performance hit immediately after failover even. But other than that, this just works. But we have another option where we can circumvent this downside that I just mentioned. Namely the thing with the cold caches, and that is to basically turn this whole thing upside down. So rather than putting DRBD onto flash cache devices, what we can do instead is we can put flash cache on top of two DRBD devices. So what do I mean by that? We would have one DRBD device, which is just your regular LUN on your big storage space, and you would have another one that mirrors two really, really fast SSDs between two hosts. And this is a feature that was added to DRBD in the 8.4 release. In DRBD 8.4, we can do multiple volumes in one DRBD resource. That is to say, we have two separate DRBD devices. They both have their own sets of backing devices. But because they're in the same resource, they share one replication stream. And that in turn means that not only are we synchronously replicating over to another node, we're also preserving write fidelity, write after write fidelity, across all of these volumes in a replication group. In other words, we make sure that not only is one of these resources or one of these devices consistent between both nodes, but in fact both are. And that's really nice, because now what we have is we get all the benefits that we normally get from flash cache, which we also get in the earlier approach of just putting DRBD on top of flash cache. But now we're getting a preheated cache on failover, which is really nice. So now we have the same quick access to the data that we need most, or that we need most often, even immediately after failover, which is really, really cool. What it does require is that we need to integrate our flash cache management into the pacemaker cluster. But what's nice is that that's already done. So so how does this, and I'm going to get to in just a second how we configure this. So how does this really help us? It's very simple. It's we can wire up a simple test case where we can read just a streaming read with a simple DD with ODirect enabled, where we're hitting the flash cache device. The first read that we're making is going to be constrained by however quick the underlying rotating storage array is, because remember, at that time, cache is cold. We simply have to hit the disk, and then presumably our disks are going to be pulling something like, I don't know, 50, 60 megabytes per second, when we stripe that, over 2 stripes, we can maybe double that. So for example, we would be reading with something like 110 megabytes per second. On the second read of that same data, however, we can now hit the cache, and then we're going to be as fast as the SSD is. And in my test, that was with a reasonably low-end SSD device. I was reading with 278 megabytes per second. But if you get a decent, enterprise SSD, that's going to be considerably faster. And then you fail over, and then you do the same read again, and then immediately after that failover, you immediately get that preheated cache, and on your first read, you're reading with those 270, 280 megabytes per second, because it's now hitting the preheated cache, which is really nice. And by the way, flash cache has several modes of operation. So one is a write-back mode, which I've been referring to up to this point, which usually means that your cache device is an SSD, something that's reasonably fast on reads and writes and persistent. But you can also use flash cache in a write-through mode, where we're not using any sort of caching on writes at all, but we can still use it on reads. And then you could be using something like a non-volatile RAM violin device if you wanted to. Or a RAM disk for that matter. Like I said, it's quite flexible. It doesn't have to be an SSD, although, of course, in most cases, it's going to be an SSD that we're using as our caching device. Now, for the pacemaker integration, an OCF resource agent for this is done. It's been submitted upstream to the Flash Cache project. It's still sitting in a pull request there. And there's a current discussion that is ongoing about it. There's some testers that came in just a couple of weeks ago. So we'll see how that holds up. But the OCF resource agent is already there. What it does is very, very simple. It just creates this device, or it loads the device with flash cache load. It has to be manually created by the administrator beforehand, but only once. And then any time we fire this up or we fail over, this resource agent automatically just does a flash cache load. When it shuts down, it does a DM setup remove, so it gets kicked out of the device mapper setup table. It's just another primitive in a CRM shell group configuration, and it's commonly ordered before and co-located with the file system that we put our data into. So this is an example configuration here. That's pretty much all it takes. We have a DOBD device. This, of course, would be a DOBD device with 2 volumes. It's still managed the same way in Pacemaker. It's just a single resource, this case named Flash Cache. We've got this clone that we use for the Pacemaker management. And then we simply have this primitive here, OCF Flash Cache. We assign a name. We give it a cache device and a backing device, and that's it. In this case, your dev DOBD 0 would be that DOBD volume that's on just a rotating disk storage array, such like a RAID, and your cache device would be the DOBD that's replicating between 2 SSDs. So if you're not familiar with Pacemaker configuration syntax at all, this is not going to tell you much. However, if you are, then you will quickly realize it's really, really simple. The way we configure this flash cache thing is just as we would any highly available file system or block device or otherwise. Okay, so does that mean that everything is fine and dandy and wonderful? I wish I could say that, but it's not quite that way. And you can help. So there's a few things that could still use some work and a few things that you want to be aware of. So one thing, if you dislike having out-of-tree kernel modules on your system, steer clear of this. Flash cache is completely out of tree. I don't think there's any effort at all to actually mainline this, which comes with all of its usual consequences, such as if no one has made an effort to actually, forward port or back port some flash cache, call signatures of functions, how it's using, certain kernel function stubs, etc., for your specific kernel version that you're running, then you might have some work ahead of you. Currently, flash cache is being maintained for the RHEL 5 and 6 kernels, and there's some community work keeping it up to date on Debian, but still, it's out-of-tree kernel code. The same thing is true for DRBD as far as that is concerned. DRBD is, of course, in the mainline kernel tree, but the mainline version, or the DRBD code base that's currently in the mainline, is equivalent to the 8.3.11 DRBD release with a few patches on top. And this multiple volumes per resource is an 8.4 feature. And that is only currently available out of tree. And I don't see that changing very soon, because the block layer merge request for 3.3 just went out a few hours ago, and there is no word of DRBD in there. So I would presume that the 8.4 stuff is not in the is not going into the 3.3 kernel. Disclosure at this point, I used to work for Linbit, which is the company behind the DRBD project, and who, by the way, own all the trademarks in relation to that. But I no longer am, and I have no additional information as to what the mainlining effort is concerned, other than what's available out on the web. So that's also just my personal interpretation. So if you completely hate out-of-tree code, you may want to give this a second thought. Flash cache packaging is pretty much non-existent. Actually, even the build environment kind of sucks. There's no support for Dester and other stuff, so it's not really configurable. I understand anyone who wants to shy away from auto tools. That's fine, but like having build scripts that are completely unconfigurable, maybe not such a great idea. And as a consequence, there's also no RPM or Debian packaging. So that's something that I'm trying to get a discussion going on the Flash Cache Dev list when I get back from LCA. But that's another thing where, if you're familiar with makefile hacking and you're interested in this, here's where you can help. If you know how to run a spec, file, or you're familiar with Debian packaging, that's another thing where you can help. And the OCF resource agent, like I said, it's there, it works, but it could use some more testing. So if you're interested in that, then go ahead, try it out. If something breaks, let me know, and I'll work with you to fix it. So that means you can help. We want you to help. So if this is interesting to you, please do help. And finally, here's our company website and Twitter, blah, blah, and I forgot to put in a slide with my own contact information. Sorry about that. It's very simple. I'm Florian@hestexo.com. If anyone needs my card, I have plenty of them on me. And finally, here's something that you can do. If you like this talk, we have this thing on our website called the Shout Box. So if we help out people at conferences or on mailing lists or on IRC or whatnot, and you like that, then you can simply go to the Shout Box, use any of your multitude of OpenID logins to log in, and leave a comment, and we always appreciate that. So with that, that concludes my presentation. I think I'm out of time, but we still have 5 minutes for questions, right?
We might be slightly over, actually, but if anybody's got a couple of questions, I will run up the back of the microphone.
Go ahead.
Yeah, just a quick question about Flash Cache. It had a problem with its write-back mode with atomic writes, or the write-back wasn't atomic, so you'd end up with torn pages when the system crashed. Has that actually been fixed? I haven't seen anything go past, and if so, how are you avoiding that in your high availability systems?
I seem to recall a discussion on that, but I don't remember the full context off the top of my head. Can you find me later and we can take this offline?
Yeah, sure.
Okay, thank you.
Anybody else? Yep.
Yep, I have a question about, well, since you run the cache on the host and not on the disk array, since you don't have knowledge about what spindles you're actually hitting with your I/O, and well, behind the disk array maybe you have 1,000 SAS drives and 10,000 SATA drives. Do you have any mechanisms to make sure that you only use the expensive cache to cache the hot spindles from, say, the expensive and hot disks, and not wasting it on slow disks further down in the storage subsystem?
So it's called flash cache because it's just a cache. What's the most used data is just what's being pulled out of this. So I'm not entirely sure where the question is headed, to be quite honest.
Well, the question is if you have a 10 petabyte spread across, say, 20,000 disks,
yeah,
where 1,000 disks are expensive high-end disks, you would in that case want to make sure that you primarily use the very expensive cache to cache data only on the expensive spindles and not
yes, and it does. Yes, and it does exactly that. It's not. Do not mistake it for an HSM solution. It's not hierarchical storage management. It really is just a cache, and it will make sure that whatever is cached or the stuff that needs to be cached, only that goes to the SSD, and what's on your backing storage is on your backing storage. That's it. We have, I think, can I take one more?
Yeah, one more.
Okay. There was one over here. Right here?
Do you have any thoughts on bcache, which is targeting mainline inclusion?
I don't have any specifics on that one, simply because I haven't had the chance to work on it. But I know it exists. And if there's something that goes, that actually goes mainline, all for it. That's all. It's not. This wasn't meant to, indicate that this is the only thing that does this. Quite the contrary. Yeah. But anything that's mainline, great, awesome. Okay. Right. So sorry for the overdraft.
No, that's okay.
And thanks. And I'll be around.
Please thank Florian.